Okay, so now we're recording. 9.1 is modeling the differential equations. And differential equations, really all a differential equation is, it's basically having a derivative with unknowns and then trying to see if we can find what the function is. Sometimes it's easier than other times, yeah, differential equations, just remember it's the derivative with unknowns. And so one of the popular things that we talk about is population growth. And so the rate of growth of population, you should remember this from chapter 3, because you guys remember everything that you've done in calculus, is that population is dp dt is equal to some constant k times the population, right? Where k is the proportionality constant and p is the number of individuals in that population, right? You guys all totally remember that, correct? Something like that. So if we go back to chapter 3, one thing that we know is that as population is growing, the rate of growth of population increases also. So if you have a small population, the population is going to grow slowly, but as you get more and more people in it, the population is going to grow that much more quickly, right? And it's not just people. It could be viruses, it could be bacteria, it could be animals, it could be all kinds of things, right? But as the population grows, the rate of that growth should grow, right? So with that, we'll go back to something that you might remember from chapter 3, and it's this. So if I have the population given time is equal to some unknown c constant times e to the kt, right? Because population is an exponential growth, which is kind of funny because I think of it as logarithmic more than exponential, but whatever, it's an exponential growth. And so what ends up happening is if I take the derivative of this, don't I get p prime of t is equal to cek of t, right? Times what? What's the derivative going to be? It should be what?
K of t?
A k, right? Just a k.
Oh, just a k?
Yeah, just a k, because the derivative of kt, when we're taking the derivative with respect to t, the t is going to become 1, so it's k times 1, which is just a k. But don't we notice that this is p of t?
Correct.
So then the derivative is going to simply be k times c of e to the kt, which is the same as k times p of t, which isn't that?
Yep.
So that's where it comes from, okay, the formula. So there's a proportionality population to the rate of growth of that population is this formula. So we'll be doing some problems that are fun with finding k, but there's one important thing that happens also that I want to talk about with populations is populations have what we call equilibrium, right? And so I'll do that. So let's say that this is the equilibrium line of our population. Typically what will happen with our, and I'll do this in different colors, population will do things like this, right? It'll grow up to that thing, and I'll try to use different colors to show you different starting points. But whenever it gets to this red line, it always flattens out, correct? Do you guys agree? Doesn't sound like you guys are too confident with that. And also, if the population is above it, it will tend towards that red line, and that red line is the equilibrium, right?
So is that like the limit?
It's like a horizontal limit, yes. So what ends up happening is our population has a natural limit to it, okay? And what that means is there's a sustainable amount that can survive, right? Our planet has this exact same thing. So if our population continues to grow and grow and grow and grow, and we get beyond what the planet can sustain, what's going to happen to people?
Bye-bye.
There's a natural consequence. There's a natural consequence to overpopulation. And that is disease, famine, and unfortunately, death. The planet can sustain what the planet can sustain. There's some morbid things that they've done where they will populate a controlled environment with animals or rodents typically, and feed them to where they sustain them, and then they'll lower the food amounts to a population that would be smaller than the amount of rodents that are in there. And what ends up happening is the rodents turn on each other to where it gets to equilibrium. We have to get to that balance piece, right? So if your population is too big, it's going to drop to where it's sustainable. If the population is small, it can grow up to that sustainability, but then it will hover at that point. We can see there are consequences to population and what it's done to our planet, right? So we need to be careful about not going over our equilibrium. Okay. But does this make sense, the idea?
Yes.
Yes. So equilibrium is what's going to be sustainable, and that's important. And that equilibrium is going to be called the equilibrium solution. Okay? Now, some information on differentials. So in general, a differential equation is an equation that contains an unknown function and one or more of its derivatives. So basically what we're given is we don't know the function, but we know the derivative. Well, if we know the derivative, can we go find the function?
Integral?
We can do the integral, right? So there are some techniques that we can do. And we'll be playing some games with that. But what if you don't have a very clean integral? We end up running into some issues, and that's one of the things that's going to happen here. Now, there's also a term called order, and the order is going to be the differential equation. Its highest derivative is the order of the derivative. So you can have first order, second order, third order, 12th order. It's just what the highest derivative is. Now, in order to be able to solve for an equation, the higher the order, the higher number of initial conditions we'll need. Okay? And I'll talk about initial conditions in just a bit, but it's important that you understand order is highest derivative. Differential equation is we're given a derivative, and we don't have what the original function is. Okay, so let's play with an example real fast and see if we can make some connections. Okay, So here is my example that I want to give you, and it says this. It says, show that every member of the family of functions y is equal to 1 plus c e to the t over 1 minus c e to the t is a solution to the differential equation that they give us. And that's a first order differential, right? Does that make sense? And so in this case, what I'm going to do with this is, instead of playing with the differential and trying to go backwards and taking an integral, what I'm going to do is I'm going to work with the original function that's given to me, right? This parent function, if you will, general case function, and see if I can actually get the derivative and confirm it. Okay? So let's play. So since I have the original function, I have this guy right here, I'm going to take the derivative of this. Okay? And since I'm going to take the derivative of this, what do I need to do? What do you think? How would I take the derivative? Anybody? I'll give you a hint. It's a fraction. Since it's a fraction, what should I do?
dy dx.
Well, yes, actually it's a dy dt, because we're talking about time.
Oh, yeah, okay.
But it's a quotient rule. That's what I was going after. It's a quotient. So since it's a quotient, I'm going to take the derivative of the numerator, and the derivative of the numerator is going to give me c e to the t times the denominator, which is 1 minus c e to the t, minus 1 plus c e to the t times a negative, c e to the t all over 1 minus c e to the t squared. Do we agree?
And then split
Yes.
up.
What's that? I'm sorry?
And then we break it up, right?
Yeah, we're not done. That was just the derivative. We haven't done anything to it yet. Right? So then from here, what I'm going to get is I can pull out a c e to the t, and I'm going to make my life much easier. So I'm going to get 1 minus c e to the t minus 1 minus c e to the t. Oh, it's actually going to become a plus, right? So plus over 1 minus c e to the t, that quantity squared. Agreed? So we can see that y prime is going to be c e to the t times 2 over 1 minus c e to the t, that quantity squared. Which, let me clean that up so it's pretty. Agreed?
Agreed.
So we saw that the derivative of this generic function is going to be 2ce to the t all over 1 minus c e to the t, that quantity squared. But the derivative that we're given was this one, right? So we're going to try to confirm that this is in fact true. But notice that the derivative here is written in terms of y, right? Do you see that? The derivative has a y variable, and everything that we have is in terms of c's and e's and t's and numbers, right? So what I'm going to do is I'm going to take this derivative, this differential equation, and I'm going to substitute because I know what y is in this case. So I'm going to go, okay, 1/2 y squared, it's minus 1, is equal to 1/2. I know what y is, right? Isn't y 1 plus c e to the t over 1 minus c e to the t, and then it's squared minus 1. Does everyone follow how I got what I just got?
Yeah. I just substituted.
Mm-hmm. It was just a substitution, correct? Does everyone see that?
Yes.
Okay. So now I'm going to do some manipulation to see if I can come up with the same equation that we had. So I'm going to have 1/2. I'll do it slowly for you guys. That quantity squared over that quantity squared, which will then be 1/2 1 plus c e to the t quantity squared minus 1 minus c e to the t that quantity squared all over 1 minus c e to the t that quantity squared. Agreed?
Yes.
Okay. And then expanding, I'm going to get 1/2 1 plus 2c to the t plus c to the 2t minus 1 plus 2c to the t minus c to the 2t all over 1 minus c to the t, the whole quantity squared. Yes?
Yes.
So that's going to give me 1/2 4, c to the t over 1 minus c to the t quantity squared, which is going to give me 2c to the t over 1 minus c to the t quantity squared. And by golly George, they are the same. You with me?
Yep.
Okay.
Just algebra.
Yeah, it's just algebra. 9-1 really is just algebra. There's nothing really too crazy about it until we get into what's called the initial condition, which I'm about to show you. Okay? So, are you guys ready, or are you still copying this down?
Still copying, just 1 second. We should always be able to prove it, or will there be a case like, oh, it's not, you can't prove it? You can't.
Well, if they're going to give you a problem where you need to show it, you need to demonstrate it. Either you can show it or you can't. Right?
Yeah.
And if you can't show it, then it's not going to be something that you'll be like, nope, it fails.
Okay.
So it's going to be a yes or a no. Right?
Oh, okay.
Don't worry, in 9.3 we're gonna really use it, but till we get to 9.3, it's just let's see if we can understand what's happening. Okay.
Okay, Professor, you can move on.
Is everyone good?
Yes.
All right. So here we go. So now using that same example, now we're just going to play a game with an initial condition. And what initial conditions are talking about is if we were to take the integral of this thing, right, we could find out what the equation was. Okay? Now, it's because we know what the actual parent function was to this, we can play the game, right? So a lot of you, probably your initial inclination is to be like, well, sir, can't we just do y prime? So if I take the derivative of that side, I can take the derivative of this side, right? Isn't that the
first thing you
gut
want to do.
reaction for you? We'll get there, but we're not there yet. And this will be a process that we're going to do, but not for this example. Wait till we get to 9.3 to do that. Okay? For this problem here, what we're going to do is we're going to, again, take the information that we already knew, and we know that y is equal to 1 plus c e to the t over 1 minus c e to the t. Right? Because we knew what the function was that we were going to use, from the original function, we can now substitute values. What do I know that y is equal to? No. With the initial condition that we have, that is this. What's y?
Y is 2.
Y is 2. What's our x? Or what's our t in this case? 0. So we're going to do exactly the hard mathematics of substituting in. Well, what do we know about e to the 0?
1.
It's 1. So I'm going to get 2 is equal to 1 plus c over 1 minus c. We're going after the specific equation that will go through the point 0,2. Because we're given an initial condition. Now, and maybe I should explain this to you a little bit better. Let's go back to derivatives from the get-go. Do you remember, and I've talked about this a little bit, y, that's terrible, y is equal to x squared, right? What's the derivative of that? 2x. Okay? But let's say that I switched it to that. If you only have this, and then I tell you that the initial condition was 0, 5, can you go back to get the original equation?
No.
Yes.
Oh, give it a condition.
We have the condition, we can integrate, right? So if we were to integrate, like you had that inkling, and this is what's going to be called a separable equation, which is 9.3, but I'm trying to show you. What's the antiderivative of 2x?
X squared plus c.
It's x squared plus some c. But now I'm telling you that x is 0 and y is 5. So I'm going to go find the specific equation at that point. Because if the derivative is just 2x, it was all those parabolas, right, shifted up and down that had a derivative of 2x, correct?
That's correct.
But once I give you an initial condition, I'm giving you the specific solution. Make sense?
Solve for C.
What's that?
It looks like you would solve for C on that equation.
Of course. That's what I'm doing in this one that I'm actually trying to demonstrate for you. But I'm trying to show you one that you would understand first. So what's y in this scenario? What's y?
5.
Okay. Y is 5. What's x?
0.
And then we're solving for c. So what is c? C. Isn't c 5?
C5, yep.
Which gives us...
The condition, initial condition,
No, it gives us the actual equation.
or the actual equation.
Do you see that? Because once we have c, here's what the solution was in general, but with the initial condition we were able to find c, which took us back to what the actual function was. So, in the example that I'm working on, now I'm going to try to solve for c. So multiplying both sides by 1 minus c, I'm going to get 2 minus 2c is equal to 1 plus c, and 1 is equal to 3c, so c in this case is 1/3. Correct?
Correct.
So the initial condition or the initial value problem is y is equal to 1 plus 1/3 e to the t over 1 minus 1/3 e to the t, which could actually be cleaned up to be 3 plus e to the t over 3 minus e to the t. Now we know the specific equation to the curve for the first order differential equation to get the specific curve. This will make more sense when I show you 9-2. So remember, it was y prime is equal to 1/2 y squared minus 1, correct? So when I take and separate this thing into an integral problem, my solution would have been this. At the point 0, 2. You guys with me?
Yes.
Pretty crazy, huh?
Are we always going to be given the initial condition of the point, basically?
Am I always going to give you the initial condition? No, I might ask you for just a general case, right? So like in that first example, when I took the derivative, if I had given you something like this and then said to take the integral of this to go back, without an initial condition, you could get back to here, but you wouldn't have the specific equation that I gave you. The reason that we got this specific equation here was because there was an initial condition.
Okay, so without the initial condition, you leave it in terms of C squared.
You'd leave it in terms of something that's unknown. right? Because derivatives end up having how many possible solutions? Isn't it infinite?
Correct. Yep.
There's infinite possibilities, and so that's the thing. And even with those infinite possibilities, sometimes with differential equations, what ends up happening is you might never find the specific solution. It may not be possible, and so what we end up doing, in a sense, is almost doing a best guess. Isn't that so satisfying? I'm being facetious. That's not satisfying at all. But this is the process that you'll do. You know what I might do is I may even pull up an example from the book to show you. Let me see if I can pull one. Maybe I should do one before I go on to 9.2. Make sure you guys are okay with this.
Did you do one from the homework?
From the homework? No, that's for you to struggle with. Come on.
Where is that?
All right, let's see if I can give you one. Okay, so one thing you might do on the homework is something like this. This is an example in the book, right? So they give you a differential equation. Oops. Right? You guys know it as DE. That's what your teachers will typically do going forward. If you had y double prime plus y is equal to sine of x, right? And then they give us... They're going to give us some options for this so we can check and see if it works. So if A was y is equal to sine of x, B is y is equal to cosine of x, C is y is 1/2 sine of x. Oops, almost messed that up. X sine of x. And D is y is equal to a negative 1/2 x cosine of x. We're going to try to see what satisfies the given problem. So, do I want to? That's kind of a pain in the butt. Oh well, it's all right. Sometimes you got to do it, right? So in this example here, we could plug in our substitution in and see what we get, right? Because we want to see that it confirms the problem that we have. So which one do you think would work if we substituted in would be y double prime plus y would equal sine of x? For each one of these, what do we have to do? Because this is where we'll find out how much you guys are grasping what I'm trying to tell you. If this is the differential equation, right here, what if they give me these possibilities as options for the answer? What do I need to do with each of the possible answers in order to be able to satisfy this equation?
Take two derivatives of them.
I have to take the second derivative of all of them, right? So we can see, like, if we did A, y is equal to sine of x. I just want to show you the process. Y prime is going to be cosine of x, and y double prime is going to be negative sine of x, correct? Right?
That's correct. That's correct.
So if I do that, don't I get negative sine of x plus sine of x? Is that equal to sine of x?
No.
A 0.
That doesn't work. Are you following the process?
Yeah, so we have to try and substitute every one of these possibilities.
Well, part of it is you should see something, right? If I take the derivative here, I'm going to get negative sine of x, and then y double prime is going to be equal to negative cosine of x. So what that's telling me is negative cosine of x plus cosine of x. Is that equal to sine of x?
No.
So bummer. Now we're delving into some other world. So y was equal to 1/2 x, was it sine of x? So now the first derivative of this is 1/2 sine of x plus 1/2 x cosine of x, right? Which will then give me 1/2 cosine of x plus 1/2 cosine of x plus 1/2 x cosine of x. Is that right? Oops, nope, I didn't take the derivative. That would be minus sine of x. And we can already see which one's going to be our solution. I think you can see it. Because if I clean this up, I'm going to get cosine of x minus 1/2 x sine of x. Right? Am I doing it right? I think I'm doing it right. And then D was y is equal to a negative 1/2 x cosine of x. First derivative is going to be a negative 1/2 x, negative 1/2 cosine of x plus 1/2 x sine of x Agreed?
Agreed. Yep.
Okay, so then double prime is going to be 1/2 sine of x plus 1/2 sine of x plus 1/2 x cosine of x. Correct?
Right.
And then we need to fill out the equation, which was that plus that is equal to sine of x. And this one cleans up to be sine of x plus 1/2 x cosine of x. I believe that's correct.
And it works.
And does that work? And it works.
It works.
So it was D. Does that help clarify the process for you?
Well, how does it work if you have the 1/2 x cosine instead?
Okay, so remember, this here is y double prime, right? So there's my y double prime. What is my y? There's my
It's a
y.
minus 1/2. Yep. And that they cancel each other out.
Okay.
The sine x.
Ah. So I'm trying to verify, right? But these are going to go away. So I know that the solution has to be D. Are we good?
We're good. Thank you for that.
I just pulled that out of the book. I just did that cold in front of you guys. So you'll notice I do a lot of that stuff where I just pull a problem out and I'm like, oh, hopefully it works. All right. That is 9-1. Do you have any questions on it? We're okay?
Okay.
All right, let's go on to 9-2. 9-2 is fun. So 9-2 is about direction fields. Most people don't call them direction fields. We usually call them slope fields. And then Euler's method, which is another way to approximate lines, which I'll show you guys, which is cool. So slope fields, or direction fields, however you want to talk about them, is basically, I don't know what the function is. Can you guys see that? So in this example that I'm going to do I know what the original function is?
No.
The answer is no. And I also don't know any initial condition to give me a specific answer. So that means, what are derivatives? What do they represent in a graph? What do derivatives represent in a graph?
The slope at any given point.
It's the slope, correct? And since it's the slope, we can take slopes at points and see if we can come up with something. So we're going to do that. So I'm going to say, okay, I'm going to say I have x, I have y, and I'm going to have my derivative, which is x squared plus y squared minus 1. Okay? So when x is -2 and I say y is 0, what's the slope going to be? Well, isn't that -2 squared plus 0 minus 1? Doesn't that give me 4 minus 1? Which tells me that the slope at -2, 0, I'll do it for you guys, -2, 0, the slope is going to be 3.
Can you go over why you chose a point -2, 0?
I just chose a random point that's on the Cartesian coordinate system. I could choose any point I wanted. I could choose 1,000,000 by 1,000,000. It doesn't matter. I can pick any point on the plane. Okay? But I'm trying to be practical right now. So let's say I use -1, 0. Again, it's just a point on the plane. What's the slope going to be there?
Zero. Right?
It's going to be 0. So then when I go back to this thing, it's going to be a flat line. That's the slope. If I use the origin, 0, 0, what's the slope?
-1.
It's a -1. So I want that to stick out, so that's a -1. What if I use 1, 0? We know 1, 0 is right here. What would that be?
0.
0. How about 2, 0?
Three. There's a pattern.
Maybe.
Do a couple more.
We need a field. And so since we need a field, we need a variety of points, right? How about we go up here to 0, 1.
Zero.
We get 0. All right. Well, what about 0, negative 1? Isn't that also 0?
That's correct.
All right. Cool. What about 1, 1?
You won.
Do you see all I'm doing is picking random points to see if I can see a pattern of what's going on? All right, what about negative 1, 1?
So 1.
It's 1. Negative 1, negative 1. It's 1.
You won, yeah.
1, negative 1. It's 1. Right? So I'm going to
Correct.
plot those just so you can see. This one's 1. This one's 1. This one's 1. Right? Well, we want many points. So what about negative 2, 1? It's 4, just so you guys can kind of see what's going on. What about 2, 1? Should be 4, right? Because since it's squares. So this is going to be even steeper and even steeper. And you can see how many points are there on a Cartesian coordinate plane.
Infinite.
There's infinitely many, correct? So we can start to see something about what's going on with this curve. Right? Part B says, all right, this was part A. Come up with a slope field. Part B says, can you come up with a graph based off of this slope field going through the origin? Well, we can see that this thing is growing, right? And the reason I see it's growing is because from here I see it's going up, right? There's this trend for it to be growing on this side, right? Do you see that?
Yeah.
It's growing, but if it's going through the origin, that means that somewhere around here it's got to turn. Do you see that?
Yes.
And then on this side, it's decreasing, but then somewhere it's got to turn. Do you see that?
Correct.
So it looks like it might be doing something like this. So it must be doing something like this. The blue line is an initial condition problem. The slope field on the left is just giving us a field of possibilities for our answers. Does that make sense?
Yeah.
Now, I actually have digital images of this one. I stole it from the book, and so I want to show you. You can have fractional points. You can have all kinds of points. But can't you see what's happening here? That this thing is growing, turning, then turning, going back up.
Yes.
This thing is doing this. If you were to do something further out, doesn't it look like it's doing something like this? So there's a variety of different curves. That this thing can have depending on its initial condition. Does that make sense?
Yes.
Is there any questions?
Do you know what this can relate to? Like in the real world?
Oh,
Like it seems like it, like I don't know, like it is relatable to something.
oh, it completely is. What do you mean? How about water flow?
Okay, water flow.
I mean, and that's just a simple one, right? I mean, there's a bunch of different things.
Electronics.
Air travel. I mean, all kinds of things. There's definitely a lot that's applied to this. But yeah, Rodney said electronics for sure. Differential equations come into play when we talk about current flow and things like that. So that will happen because we know that electrons don't travel in a straight line. Most people think that electrons just travel in a straight line from point A to point B, but they actually bounce all over the place, which is interesting. Now, this is what the solution would have looked like going through the origin. Do you see that? So if we'd slightly changed it, we can see we could have had something that looked like this over here. At the point 0, 1, all of a sudden our curve, instead of being like a max and a min possibility, it almost looks like a cubic. Do you see that? So slope fields impact what the potential solution can be. And do you see how much work can be involved in finding slope fields? Your calculator probably doesn't have it. I have a program on mine. Had we been in class together, I would have shared with you the program, and you could, on your TI-84, generated slope fields. But since we're not together, unfortunately I can't give you that program. But does it make sense how many different possibilities there are for slopes within a plane?
Professor, when we graph it, do we always use the y equals 0?
No, I'm going to give you, that's what I'm trying to say. How many possible answers are there to this slope field? There's infinitely many, right? Because I can change what the initial condition was. So in this example here that I gave you, it was 0, 0 was the initial condition, right? Because I told you it was 0, 0, 0. So you can see that the curve was going something like this, right? You can see that flow, if you will, of water is going this way, right? Do you see that?
Yeah.
But if I went here, look at how it changes. It's flat. That means I got to go to this one, which takes me to this one, which takes me this way. And then look. Is it the same kind of curve? It's totally different.
Yeah. Depending, you could be at sea level. If you're at altitude, yeah, that's where different impacts can be on water flow.
Well, I mean, I'm not. That's just whatever. But for this graph here, whatever this represents, wherever I'm hitting the problem is how this is going to be impacted. So if I had done it here at 0, -2, just looking at this, it looks like it would have gone like this. Almost like a tangent. Do you see that?
Okay, so maybe sometimes the problem will say graph so-and-so at the initial condition.
Yes, that's what's going to happen is you're going to be given an initial condition so that you get a specific equation.
Okay.
Provided solvable. Okay? But I wanted to take you through the process for you to be able to see that creating a slope field is just plotting a bunch of points. Make sense?
Yeah.
Okay.
First, just a question regarding that. Does that have to do with understanding of the constant, like the plus c in every an integral, and where that's where the multiple possibilities come into play?
Well, it's just simple. I mean, let's just go to y equals x squared, right? Or forget it. Let's not even look at it. Let's look at it from the derivative perspective. So if I said dy dx is 2x, right? When I go to do a slope field for this, the derivative at 0 is 0. Anywhere along this, it's going to be 0, right? Along 1, it's always going to be 2. Right? Along 4, it's going to be 2, x equals to 2, it's going to be steeper, right? And then it's going to follow that same pattern on this side, but negative. And then a little bit steeper negative. Right? And it's just going to keep blowing up and blowing up and blowing up. The initial condition for this problem is really just going to impact where that parabola is. Does that make sense?
Yes.
So dy dx equaling 2x is just going to give me some slope field. Right? I'm not going to know anything about that slope field until I say, hey, give me a possible graph of what it looks like at 0, 3. Then I know what to do at 0, 3.
Correct.
So that's all the slope field is telling us. Okay? All right, let's go on to Euler's method. So Euler's method is just basically telling us we're going to take a derivative with some condition, and then we're going to take the derivative again as we shift increments. So from Calc 1, one of the things that you did, if you remember, you don't have to write this down, I'm just showing you. If I want to do an approximation of a curve, right? And I said, okay, this is the point 3, 9 for the function y is equal to x squared. I could take a derivative, if you remember, right? And I could do a very good approximation of my function by plugging in a number that was close to my a. So my a in this case was 3. I could have used 3.1 and use the derivative to come up with a very good approximation, correct? Do you guys remember that from Calc 1? So the derivative would have been 2x. Then writing the equation, I would have gone y minus y1 equal to 2x x minus x sub 1, right? Having our derivative.
Correct.
And then if I said, okay, it's 3, so I'm going to use the 0.39. So y minus 9 is equal to, let's say 3.1, right? 2 times 3.1. And what do we get? We get y minus 9 is equal to 6.2 times 0.1. That would have given me, hold on, I'm messing up actually, my bad. Because I want to be able to explain this to you with approximations. So if I'm going to use 3.1, the slope here is going to be 3.1. The slope is going to be 6.2, correct? Oops, this way. And then we should get the initial of this is equal to this. What is that? 18.6 minus 9, or oops, plus 9, which should give me 6.2x minus 9.6, correct? Did I do that arithmetic correct? I might not have. I think it is. Let me just double check my numbers.
Yeah, it's great.
Okay. If I plug in 3.1 into this, oh no, I'm sorry. This is just at 3. So this should just be 6. I'm sorry, guys. This will be 18. This will just be a straight 9, and then I'm going to plug in the 3.1. So when I plug in 3.1, I'm going to get y is equal to 6 times 3.1 minus 9 is going to give me 18.6, I'm sorry, and I'm going to get an approximation of 9.6, right?
Correct.
Okay, what is 3.1 squared? Isn't that 9.61?
Yeah.
So we can see that my approximation that I'm using is an under approximation of the actual value, and that makes sense because the red line is below the actual function, correct? Now, what ends up happening, though, problematically, is if I use this one curve and I go further away from 3, so let's say I went to 3.5, isn't my approximation going to be far under?
Correct. It will.
So what ends up happening, what Euler did, is as I move, I need to take different derivatives along the way to follow the curve. And then I reevaluate as I follow the curve. Does that make sense to everyone?
Yes.
Okay, so let me show you this this was chapter, I think, this approximation stuff, I think, was in chapter 3. But now Euler's method, which is so cool, is kind of the same premise, but we need to, like I said, take more derivatives along the way. So in this example here, we see that we have a step size of 0.1, okay? And the step size we can see is our h, right? So we know h in this case is going to be 0.1. Our x naught is given to us. What's that? What would x naught be in this problem that we're given?
0.
It's 0. What's y naught?
1.
1. And then f of xy is the derivative function that we're given. Okay? So what's going to happen here is we're going to generate values to find approximations of the value of the actual function. Does that make sense?
Yes.
So let's start. So y1, right, following this pattern right here, y1 is going to be equal to the initial y value that we know plus our step size times our derivative function. So that's going to equal 1 plus 0.1 times x plus y. Well, what's my x in this first step? It's the building block one, so it should be the initial. So it's 0. What's the initial y? 1. And so we're going to get 1 plus 0 times 0.1, which is going to give us, well, 0 times this, which is going to give us 1.1. Okay? This is our y1. Based off of the derivative, like I did with the x squared, it would be like that 3.1 example that I gave you. Does that make sense? It was a slight under approximation by a hundredth, but it's pretty good approximation, right? So in the next step, and you guys should be able to see what this is, right? Doesn't this look like slope-intercept form?
Yes.
Yeah.
That's funny, right? But it is. The next one then would be y sub 2, and I'll write this down. Y sub 2 then should be y1, because now we're going to take the derivative evaluated at the next step size, right? Plus our step size evaluated at the derivative of our function. So in terms of the derivative, that is the slope field that we're using. Make sense?
Yes.
Okay. So what is y sub 1? It's 1.1 plus 0.1 times what's now our x sub 1.
Is 0.
What's that? I'm sorry? No, what did you think it was?
I would say the y would be with the 1.1, and then we use that to solve for x.
That's 1.1, but then what's my x? How did x move? Didn't it move a step size? So if I'm at 0, right, and I shift over 0.1, what's my new x?
0.1.
0.1. The step size is how x is shifting. Does that make sense?
Yes.
So I'm going to get 1.1 plus 0.1 times 1.2. And that's going to give me 1.1 plus, what is that? 0.12,
Correct.
which will give me 1.22. Can you find me 1.3? That's it. 1.362. Was everyone able to get it?
Yeah, I just got that. Just got that. Correct.
Does anyone need me to show it?
I got it as well.
All right. So y of 3 is going to be 1.22 plus 0.1 times 0.2 plus 1.22, which is going to give me 1.22 plus 0.1 times 1.42, right? Which will then give me 1.362. Now, is this a very good approximation? Of the values of whatever this curve looks like? Is a tenth of a move, a tenth of a whole number, a good step size? It's pretty good, right? It's better than a half step size, right?
Yeah, that's correct.
But better than a 0.1 step size. A 0.05 would be even better. Does that make sense?
Yes.
So the smaller your step size, the more accurate your curve will be. So, let me show you a picture to this problem so you guys can get the idea of what I'm trying to talk about. Ready? This here is the picture of the function of that example. Each one of these is representing a different step size. So the one that we did is this, like, I don't know if you can see it, it's this h is equal to 0.1. It's this, like, blue line. Can you see that?
Yes.
And then there's even a better line, which is that red line there. That red line is for h is equal to 0.05. Oh, I'm sorry, 0.005, which isn't bad. Just so you can get the significance, this one is an h step of a half. Can you see that there's issues? Our approximation here ends up being, it's veering away from what the curve is doing, correct?
Correct.
So the smaller the step size, the better Euler's method will be at giving us approximate values that are very close to the actual function's values. So we can use Euler's method for approximations. Does that make sense?
Yes.
Anyone besides Rodney?
Yes.
You guys are just like, I got to do the homework and see. Okay, well, the smaller the step, the more accurate it's going to be. And it's pretty sweet. I had to zoom in to be able to show you that number. And then I zoom out and it becomes hard to read. And that makes sense because the increment is so small that the accuracy is so close. Right? And that's the process to Euler's method. All right? Okay, so this is what I had for today for you guys. These two topics. I'll upload the homework for you in just a bit. Do you have any questions for me in terms of the homework that we've already assigned? Or is everyone still trying to do homework because they were Lakers distracted this weekend?
I had trouble with the one that was a variable, with the a/7.
Okay, let me see. What number was that?
It was number 6 for me.
Number 6? Okay, let me log in and see so I can pull up the problem. And this was on 8.2?
Yeah, 8.2.
Okay. Let me see. And you said number 6, correct?
Yeah, number 6.
All right, so here we go. Homework review. All right, this is 8.2, number 6. And it says the curve is rotated about the y-axis. Find the area of the resulting surface. So they give me y is equal to 1/3 x to the 3 halves and my interval is from 5 to 12, correct?
We probably had a different one then.
Yeah, I mean, you have different numbers, but...
No, the problem had a variable of a in it.
Oh, I'm sorry. I was doing number 5. So, my bad. I just look at the problems and not the number. It would help if I looked at what problem number it is, right? My bad. Okay, so here we go. So in this problem, the equation that I get is x is equal to the root of a squared minus y squared from 0 to a over 7. That's what I've got. All right? And it's asking for us to rotate about the y-axis and to find the area of the curve, of the surface area, right? Resulting surface area. All right, no problem. So what do we need to do first? Huh?
Take the derivative of that.
We got to take the derivative. So we're going to get dx dy is going to be equal to 1/2 a squared minus y squared to the negative 1/2. And then by the chain rule, a negative 2y. Agreed? Aaron?
Agreed.
Yeah, you got it.
Okay. So that should give me a negative y over a squared minus y squared. And I'm just going to keep it as a 1/2 power. It's in the denominator, right?
Yeah, it's a negative.
Okay, cool. So then from there, I know my surface area is going to be the integral, and it goes from 0 to a over 7. Yes? Two pi, and it's going to be x, because we're rotating about the x-axis. So that's going to be root a squared minus y squared, root 1 plus the dx dy squared. Agreed? Aaron?
Yeah.
Okay, so then that's going to give me a negative y over a squared minus y squared. That's to the 1/2. That whole thing squared. And then, of course, this is going to be dy. So now we got to do the algebra, right? So integral 0 a to 7 2 pi root a squared minus y squared. This is going to be 1 plus y squared over a squared minus y squared dy. Yes?
Yeah.
0 a to 7 of 2 pi root of a squared minus y squared of a squared minus y squared minus y squared, plus y squared over a squared minus y squared dy. I'll just put the 2 pi out out front already. Do you see something cool?
Those cancel.
Yes? Oh yeah, let's not forget the 2 pi. My bad. And doesn't that give me 2 pi a times a over 7, which will be 2 pi a squared over 7. Does that make sense? All right, cool. Any others? Or do you guys just need homework catch-up time?
Can we do number 8? This one's
No, I don't think so.
here.
Just kidding. All right, let's see. So number 8, you said, correct? All right, so this is number 8, same section. I have 9x squared is equal to y squared plus 27 from 3 to 7. And we can see this is, what is that, type of ellipse? No, it's a hyperbola, right? Hyperbolic curve. Too fancy? Well, it's a hyperbolic curve. And so we know it's symmetric, right? So we can use some symmetry here. We can mess with this and just use one side. Okay? So I'm going to mess with it and get... I'm going to get this. Do you see how I got that?
Yes.
Yeah.
You're okay with that? Okay, so then from there the derivative of this, because this is what I want to play with, is going to be 3 over 2 x minus 3 to the negative 1/2. And then I can go surface area. So it says from 3 to 7 of 2 pi three root x minus 3, right? Because that's our y in this case, since we're going about the x-axis. And then we need to do the root of 1 plus, what do we can get? 9 over 4 x minus 3 dx. Excuse me. Okay, so how do I want to do this so you can clearly see this? All right. All right, let's do it. I'm just trying to think algebra. Actually, let's just call that a 6 real quick. And then here, the wonderful algebra comes into play. See if this will help us. What is that 12 plus 9 over 4x minus 3. What does that do for me? Jeepers. Oh, I can pull out a 2 in the denominator and then have over root x minus 3. Right? And then how do we integrate this?
Correct.
How do we integrate this?
The U sub?
Yep, u sub. So u is going to be 4x minus 3. So du is 4 dx. So 1/4 du is dx. And so I'm going to get 3 pi over 4 root of u. Do you want to change the values?
Yeah, mine.
All right.
Yeah.
So if you plug in 3, I'm going to get 12. This is going to be 9. If I plug in 7, it's going to be 25 du. And so that's going to be u to the 3 halves. So multiplied by 2/3. That's 3/4 over pi. Divided from 9 to 25 is going to give me pi over 2 times 25 root 25 minus not 9 root 9. 125 minus 27. If I did that right. What is that, 98?
Correct.
Which is 49 pi for Christmas. Cool?
Thank you so much, Professor.
Yeah, no problem. That's my job. Does it make sense, the steps I showed and everything? I try to show every step.
Yes.
Yeah, it makes sense.
Okay, cool. All right, anything else, or do you guys want to go hop on the homework land?
I have one. I
Okay.
kept running into an issue that I feel like I need to just get it straightened out, because sometimes the problems are just like, it just wants you to plug in like the variable y instead of plugging in x equals, like for number 4, I had x equals 1/3 y squared times y squared plus 2 to the power of 3 over 2. But instead of like plugging that in, like by multiplying it like into the formula, it just wants you to plug in y, and I wasn't sure. I don't
You
know
said
if I-
number 4 on 8-1?
A2.
Oh, 8-2. Let's see. Am I in 8-1 or 8-2? Oh, this is 8-2. Okay. Yeah, I'll do it. Number 4?
Yeah.
Okay, so here's number 4. And my function is x is equal to 1/3 y squared plus 2 3/2. And mine's going from 1 to 5. Okay? Okay, so we have to take the derivative. That you could do, right?
Yeah. It's just the part where you plug it into the formula.
Okay, so when I take the derivative, the 3's are going to go away. I'm going to get this 2y So my derivative is going to be y squared plus 2. Yes?
Yes.
Oh, shoot. Almost forgot the 1/2 power. Come on, man. Check me. You got to check me. Okay, so then from there, when I go to get the integral, it's going to go from 1 to 5, right?
Yeah.
And what do we have here?
2 pi y. But that's the problem. That's the part that
Okay, what is it about that you don't get?
like what I was initially doing was I was plugging in the x like 1/3.
Okay, so one of the things that's important is what are we rotating by? We're rotating this problem about x. And so when we're rotating about x, the radius is in terms of y.
Why, right?
Yeah. So when we rotate something this way, this is the radius. Right? If it's being rotated through here. So this is your y. Remember I drew those pictures?
Yeah.
And then when you rotate here, your radius is this way. It's going to be a
x. And then that's when you plug in the
2 pi x.
Okay. Got it.
Cool?
Yeah.
All right. So
I
you
needed that straightened out. That part.
Oh, okay, cool.
Because I would do it wrong, and then I'm like, what did I do wrong? And then I realized I was supposed to plug in y.
Yeah. Just think about which way is it being rotated.
Okay.
All right. Any others? There was 10 of you at one point. Now people are gone. Man, no love. They're like, ah, he's recording. Who cares? I see. It's cool. All right. Well, I guess I'll stop recording, and then I'll just, if you have something for me to do, I'll do it. And if not, we'll just sit on the computer and look at each other. All right.